Okay, so we move fast. Each lecture has a theme. I've delayed introducing electronic spectroscopy because it's more complicated. But there's a reason why we do electronic spectroscopy, and that's because these electronic transitions have higher oscillator strengths. So if you're lucky enough to have a molecule that absorbs an accessible wavelengths in the ultraviolet or the near IR, it's more, the oscillator strengths are bigger and the detection capabilities are much better. It's also true, though, that the lasers are much more expensive. So the nice thing about tunable diode lasers that we'll talk about lecture 3 today, economical, portable, robust, but the infrared transitions are generally weaker. But on the other hand, there's a lot of combustion species that do absorb, that are highly populated and do absorb. Okay, so we're going to talk about electronic spectroscopy kind of quickly, and then we're going to do, in the second lecture, I'm going to do a 2 case studies. So we won't be able to go through it in great detail, but I've tried to be complete. If you had to calculate one of these line strengths, so the picture on the right is a plot, it's called a Fortran plot, where we use M to represent J. So M is J plus 1 on the R branch, and M is minus J. So this is a plot of J, really, versus frequency, and the positions of the lines. And you'll notice that there's a P branch, there's an R branch, and there's a Q branch. So all that means is that we've looked at a situation that allows delta J of minus 1, 0, and plus 1. And it'll be interesting to see which of these branches is the strongest. And you'll see that's why that's important. So anyway, this would be an example of what, if you wanted to study a new molecule, let's say it's NH, because ammonia is popular right now. Ammonia decomposes to produce NH2 and produce NH. So if you wanted to calculate the spectrum of NH, as one of my students is doing now, you would calculate the positions of the lines. You would then calculate the strengths of the lines if they had not already been done by someone else. Now you know the position and you pick the strongest one. Then you worry about the line shape and you're ready to go. So we have to be able to do something like this, or at least understand the plot that's been made by someone else. And just like there were models for polyatomic species, structures, different classes of molecules, we also have models for electronic transitions. When we talk about electronic transitions, what's happening is we're worrying about the change in the contribution of the electron spin. Things are always, angular momentum is quantized. So far, we haven't really talked about the angular momentum of the electrons. So all we're doing now is adding angular momentum of electrons in the ways that quantum mechanics allows, with the transition selection rules that they allow. So it is a little bit more dense, but you'll see the power of it. And of course, if you're just following somebody else's work, you may just have to accept what they've concluded in terms of the wavelengths and the line strengths and so on. What we're worried about is how do you get the spectral absorption coefficient so that you can use it. Okay, that's where we're headed today in this first hour. So this is what's called the term symbol. This is a symbol which the spectroscopists would look at, and it tells them a lot about the quantum states that you're concerned with. So some of you may have seen this. So and it turns out the symbolism is similar for atoms, atomic spectroscopy, and for molecules. So for the atom, we would have a symbol like this, superscript, subscript, and primary. And there's a meaning. S stands for spin, which for single electron is 1/2. So that's the spin, because it turns out the spin, molecules have to transition between states that have a common spin. And orbital angular momentum, and then J is always the total angular momentum. Now we go to diatomic, it's kind of similar. Instead of L, we now use lambda. Instead of J, we may have an omega. Spin is the same. So we're introducing you to this notation. And the simple interpretation, so L is quantized 0, 1, 2. And that's labeled with SPD. So you go from the symbol S, which means that L is 0. So there's a symbolism. Now lambda corresponds to the angular momentum. But it's because it's now a molecule, there's a preferred coordinate along the, we're talking about diatomic molecules, so there's a unique axis between the two nuclei. Turns out that the only thing that really counts is the component of the angular momentum along that internuclear axis. So that would be just like we have L over here, we have lambda 0, 1, 2, and this got this SPD sigma pi delta. So pretty simple to see the analogy. S is the total electronic spin angular momentum, because remember, this is all about angular momentum, and we're going to combine different kinds of angular momentum. Like we had the symmetric top, and we combined two components of angular momentum. So S, the spin of a single electron is a half, but it therefore combines to be half integer values. Now for the molecule, so sigma is analogous to L. It's the projection of S onto the internuclear axis, and it has constraints. And the reason for these constraints is that if there was a field present, quantum mechanics would tell you that these vectors can only take particular orientations. So these rules from quantum mechanics. And in the case where you have combinations of spin and orbital, so we have two components of electronic angular momentum, spin and the orbit. So the electrons are orbiting around while they're spinning around their own little axis. And so omega would be the sum of these projections along this axis. Quantum mechanics will call, quantum mechanicists will call this they'll call these the good quantum numbers. It means, so when there's an axis between the two nuclei, it's only those projections. Now remember, these are models. Models are approximations to reality. They're not necessarily reality, but they're models which allow you to do the computations and to predict how things behave. And we'll find that in some cases, we're going to pay attention to OH in the second lecture, that, well, the model doesn't quite fit. So we use kind of an intermediate model. Okay, nitric oxide. So nitric oxide, important species, would be labeled with a symbol X2 pi. Capital X, the precursor, of course, means it's the ground electronic state. Now you've learned that 2s plus 1 is 2, so s is a half. Pi, now you've just learned, sigma pi delta means that component is 1. So s is a half, lambda is 1. Now omega, which is the combination, will turn out to be, therefore, 1 plus a half and 1 minus a half. So there's two possibilities. So you get one vector and the other can either add or go opposite. So that just means that nitric oxide in the ground electronic state X, there are actually two types of molecules. The lambda, or the omega equals 3 halves and the omega equals 1 half. What's the difference? The orientation of this spin. So they're called spin split states because they have rather similar energies. So these states, these are like two separate molecules that are almost the same, but one of them has a spin that points in a different direction. And that makes a difference. So that means their separation is only 121 wave numbers. And hopefully you've remembered now that I can go from wave numbers to temperature by multiplying by 1.44. Therefore, the characteristic difference in spacing expressed in temperature units is 1.4. In other words, it's a couple hundred degrees. Therefore, at even room temperature, there's nearly equal populations in these two molecules. So they're both nitric oxide, but they're electronically different. And therefore, we have to treat them as different. Carbon monoxide, another important species. Carbon monoxide is an X1 sigma plus. Don't worry about the plus. X tells me it's the ground state. The 1 tells me that there's no spin. The sigma tells me there's no orbital angular momentum. Therefore, I don't even have to actually worry about the electrons anymore because there's no contribution from them. So that turns out to be the simplest case. It's great when you have an X1 sigma. Life is simple. This will turn out to be the same as the rigid rotor molecule we've already talked about. So when we talked about CO, rigid rotor, heteronuclear, did the rho vibrational spectra, now it's going to be the same because the electrons have no contribution in this case. It's the easiest case. Oxygen, another important species. It's an X3 sigma G minus. Don't worry about the G and the minus. That means we're looking at the ground state, and the spin now is 1, and the orbital angular momentum component lambda is 0. So now we've looked at 3 different examples, and these correspond to 3 different models that we use. These, you'll at least wonder, what are these things? They all have to do with symmetry properties. And quantum mechanics tells us that states have to have a certain compatibility for there to be transitions. So these parameters will constrain the selection rules. If you go from a certain state with these properties, you can only go. So just like we had delta J plus or minus 1, and then we're going to find delta J of 0. There are certain constraints that come back to the symmetry properties. We're going to find out that this one is called Hund's case. This last one's called Hund's case B. So Hund is the physicist who gets the credit for having established these primary models. Hund's case A, Hund's case B. And so that's just the name that's given to specific models that we use. So this basically boils down, there are basically 4 of the most common molecular models shown here. If lambda and S are both 0, we're going to find out it's the same. We already have done it. We've already done the rigid rotor. If, on the other hand, lambda is unequal to 0, so anyway, there's 4 possibilities here. These are the 2 in which spin are not 0, and they cause trouble. Hund's case A and Hund's case B. So right now, we're going to do, looks like we're going to start with rigid rotor and symmetric top to get started. So what are we doing? We're folding in the angular momentum of the electrons. And as quantum mechanics, it tells us that angular momentum is quantized. And there will be some so-called parity and symmetry numbers that will constrain the selection rules, but in the end, we're just going to accept them. We're just going to accept the rules that quantum mechanics gives us. So now, let's do the 1 sigma. We're back to the same thing we did when we did rotation and vibration. We have a diatomic molecule. We know the molecular weights of the nuclei, and we're going to look at the angular momentum. And if we had any, we would have to add in the role of the electrons. But there's no role for the electrons along this unique axis. Remember, the A-axis is always the unique axis. You start there. B and C are just orthogonal, passing through the center of mass. So in fact, in this case, there's no definition for omega. The 1 sigma case is the easy one. Lambda is 0, means there's no component along this axis. The spin is the same. So basically, we're done. We've already done this before. We got the rotational expression. Remember, the D is a small term that you only worry about if you're trying to be precise. That's the energy. F, always F for the rotational energy. B, which we recognize has a slight dependence on V. We keep that expression vis-a-vis. Total energy is always the sum of, now, rotation, vibration, electronic. Why, when we did the vibrational motion in the ground state, we didn't have to talk about T sub E because it's 0. When you go to new electronic states, they each have their own TE. Within those wells, they have their own rho vibrational spectra. But now we're talking about transitions between different wells. So we have to keep track of the T sub E. And as always, the change in energy between the allowed states is the photon energy. So it's always conservation of energy. Delta E is the sum of the differences. So if you stayed in the same electronic state, this term would be 0. But we have to keep track of all. These are the 3 internal energy coordinates that we worry about. Okay, so the rotational energy is simple. Total energy is this. Energy change is the sum of the differences. What are the selection rules? Well, we've seen that one before. They're exactly the same because electrons play no role. We're lucky. Now, we have to be a little careful. This is for a specific electronic state. We also have to pay attention to the term symbol for the excited electronic state, which may be different. But within this state, within this term symbol, we have these rules we've seen before. Now, so for rho vibronic spectra, That's row vibrational. Okay, I use rotational. Row vibrational to me means the combination of rotation and vibration. I use the term row vibronic to mean the combination of rotation, vibrational, and electronic. So when you go between two electronic states, you have to worry about the change in all three, rotational, vibrational, electronic. So I call that row vibronic. Not everyone uses that terminology. Now, what happens to, turns out that delta J continues to be plus or minus 1. But now I'm going between two electronic states. What's delta V? Well, delta V is no longer just 1, as it would be if we were staying within the same electronic well. We're going between electronic states, and I explained to you what is called the Frank-Condon principle, that molecules want to change electron characteristics at the same internuclear spacing because the electron changes so fast. There's no change in the internuclear spacing. So basically, the transitions favored are those which are right above each other. But they're not always right above each other. And so there's something called the Frank-Condon factor, which says that if you're in a given V double prime, and you have choices of V prime in the upper state, where you're going to go. Well, you actually have choices. And it's all done very nicely so that the Frank-Condon factor talks about the propensity of a specific V prime. But the sum of these Q's is 1. So it's like a fraction. You're in a given electronic state, the given row vibrational state. You go to this excited state, and you have choices. And it's all done in a way that which fraction goes here, which fraction goes there. And you're going to learn, you'll hear, if you learn, you're going to learn that the total probability of going from one state to all of the above states is the electronic oscillator strength. So the oscillator strength, which comes back to us again, is total probability. Or putting it another way, if you're in any excited state molecule, in a given quantum state, the sum of all your possibilities for A is FEL. So FEL has a real nice meaning that we'll learn more about today. Now, I always use this notation of delta J plus or minus 1. There is in literature, sometimes people will talk about delta being final minus initial. But I think it's cleaner just to talk about upper minus lower myself. But in the literature, you're going to find there's different papers will sometimes use different rules. So this is a question that people have been asking, which brings into us the Hanson factor. So people are saying, well, why is maybe they're asking, why is the R branch a little bit higher than the P branch? What's the relative intensities as we go across the distribution? I try to introduce this as assume everything is equally probable. That is, assume that if you are an individual molecule in J, your probability is the same as any other J. But there's more through the Boltzmann distribution. So in my simple model, the P and the R branch would be equal. And they would just mirror the Boltzmann distribution. But there is something called the Hanson factor, which puts this right. And it just slightly adjusts, and we're going to learn about that today, or I'll talk about it anyway. So basically, the key for emission or absorption really is the Boltzmann fraction in that state. If you have a higher Boltzmann fraction, you're going to have a higher propensity for emission or absorption, slightly modified by this Hanson factor, and also impacted by what's called the Frank-Condon factor. So if you asked if I'm in a given lower state and I undergo a transition to the excited state, for a given V prime, what's the relative contribution to another V prime? That's just the Frank-Condon factor. And it's a number, and they're known, they're measured. So it turns out it's actually a nice system once you get used to it. So it turns out for us, fortunately, many of the stable, we're doing diatomics. We're mostly doing stable diatomics, whereas OH or NH would be unstable. They're not stable molecules. But if we have a stable molecule, it's carbon monoxide, chlorine, bromine, nitrogen. Turns out they're all rigid rotors. We're lucky. Those are the easiest ones. You almost can forget the properties of the electrons. And even though we have the possibilities of sigma pi delta or SPD, sigma pi delta, it turns out that there are no ground states with a delta. So they're only sigma and pi. Good. So life is getting a little simpler now. So for the rigid rotor, we don't really have to worry about the electrons. It doesn't complicate the spectrum. And they're mostly either sigma or delta. So even though there's a lot of apparent possibilities, there's only a few real possibilities. Now, it turns out somebody might ask the question, well, what happens when you go to triatomic? Well, life gets harder, and the symbolism changes a little. Usually there will be a tilde on top of the X, and so on. But it turns out that HCN, somebody was working on HCN over here. HCN and N2O, but you're doing the infrared, probably, okay. But HCN and N2O is an important one. That's nitrous oxide, that's laughing gas. That's formed when you have combustion with some N2O, NO. They're all rigid, 1 sigma. So actually, in many cases, spectroscopy is not that hard. But when it gets hard, it can get hard. Oh, now, anybody here know about the role of nuclear spin? So we did the angular momentum associated with rotation, vibration. Now we're doing the electron contributions of spin and orbital angular momentum. And you've learned that quantum mechanics cares about symmetry properties. And it cares about angular momentum. We talked about, we just introduced the spin of the electron about its own little axis. Oh, what about the spin of the nuclei? Turns out they spin too. So it's all about angular momentum, and now we're keeping track of all the types. And in fact, there is a contribution from nuclear spin. But the good news is, if the molecule is symmetric, like nitrogen, molecular hydrogen, not a factor, forget about it. It's only when there's an asymmetry that you have to worry about this. It's only when there's a symmetry you have to worry about this. If it's asymmetric, like CO, NO, you don't need to know about nuclear spin. Molecular nitrogen, molecular hydrogen. So you will have heard about, for hydrogen, ortho and para. That's what this is. So the contribution of the nuclear spin, even though you might not think it's very big, is that because of quantum mechanics, certain states can't exist, or certain states have different degeneracies. So if the molecule is symmetric, turns out we have to worry about something called nuclear spin. Symmetric top, okay, we did the simple case, the rigid rotor. The symmetric top case is quite a bit like the symmetric top we did for low vibrational, or for rotation. And so now we have the unique axis that we care about, where lambda is now the component. What's lambda? It's the component of the orbital. So the electron's orbiting around this molecule. And you only care about, and has a certain amount of angular momentum. And it may point in different directions. The only thing you care about is the amount that corresponds to this axis in this model. So that would be the component. Meanwhile, we still have the angular momentum of the molecule that rotates around the center of mass up due to the nuclei. In this case, since we have to preserve J for the total, we no longer use J, the momentum about that B and C. So we now substitute N. In a limit that there's no lambda, we're back to using J for the total, and it's just the nuclear motions. But now what you have is you have a component of angular momentum here, and you have one here, and so you have to find the sum. So the J is the total. It's just a combination of two types of angular momentum: the nuclei, motion, the masses, and the electron. So now J, which always we use for the total, is pointing in some new direction. This is interesting. You know, we always talk about the angular momentum, about the B axis, which is perpendicular, and the C axis, which is orthogonal. The A axis is the unique axis. What about the angular momentum about the A axis? Well, we got point masses, so it has no angular momentum. Well, that's a model. There actually is some angular momentum. But because the quantum spacing associated with that is so big, it's effectively the angular momentum is zero. So we get n for the angular momentum of the nuclei, lambda for the projection of the orbital electron motion, and J is the total. So this is our symmetric top. Remember, the symmetric top, it spins about its own axis while it precesses around the vertex. It's got like two coordinates. And that's really, it's exactly the same thing as that case. Okay, so now what do we have to do? We have to find the energy expression of the ground state. We have to also find the energy expression of the excited state and then take the difference. So the rotational energy now is going to, remember F is still the rotational energy. Now is the combination of B, JJ plus 1. Remember this term. Remember we had the oblate and the prolate. It's just the difference between the momentum about the A axis and the B axis. Now, a few things get to be a little tricky. So the parameter B, you now know, was h over 8 pi squared I. That's a B. But I just got through telling you moment of inertia about A is kind of small. But there is a finite value of A. And so, and this is where we kind of wave our hands a little bit. There is an effective angular momentum. So there is a value for A. So everything depends upon the difference between these two. And it may be that one of them is much bigger than the other. So since the moment of inertia about that axis is small, A is actually the big number. And we don't have a physical meaning. We don't have a physical interpretation of the moment of inertia about A. But it has an effective value that shows up in the spectra. Turns out it's a big number. Now this also is a reminder that you have to have when you have two quantum numbers now, when you have two coordinates, you have to worry about the distinction between values of J. J can only be, J can't be less than lambda. I didn't say that very well. Whatever lambda is, it's a number. Whatever it is, J can't be smaller. Remember, we have J and K. K can be all the way up to J, but not more. J has to be equal to K or bigger. That's all that is. So this means that certain lines will be missing when we look at the spectrum. So this expression right here is completely analogous to our polyatomic model for the symmetric top. So now we have selection rules, which come to us from quantum mechanics, and which for the rigid rotor, delta J of 1, plus or minus, electronic transition, delta J plus or minus 1, delta V from Frank constant factors. So now for our symmetric top, where we now have, remember, the spin is 0, but we have a finite value of lambda, which appears here. So when lambda is 0, it goes away, we're back to rigid rotor. When lambda is here, we got to put this in. The selection rules are delta lambda is 0. So whatever the lambda is in the lower state, it's got to be the same in the upper state. It says. And delta J is plus or minus 1, and now can also be 0, but that one's weak. Okay, so I didn't say that right. Delta lambda of 0 has these delta J rules. Delta lambda can be plus or minus 1, in which case I get some new rules that turn out to be the same, except in this case, delta J is really weak. So because of this, we now have Q branch. And the difference between the rigid rotor and the symmetric top is that now there's kind of like two band heads. So it looks a little more complicated. But it's actually very similar to what we've done before. So how do we go about this? We always add up the energy and the energy T prime in the upper state. There's the rotational term, which now has this symmetric top part, plus the vibrational term, plus the TE prime. The lower state, same thing. So this is assuming we got symmetric tops, top and bottom. And of course, TE double prime, if we're looking at absorption from the ground electronic state, TE double prime would be 0. And the energy of the photon is nothing more than the difference between the two states. So I have a P branch, I've got an R branch, and now I have a Q branch. And as always, you just take the difference between the upper state and lower state. So there's a new infinity. So I'm looking only at the rotational distribution. I have to keep track of okay, I skipped over this. So what is nu? This is the difference between the upper state and the lower state for J of 0. So if you separate out that term, that's the vibrational and electronic term. Separate that out, only doing rotational analysis. In the rotational, remember we had the working example that I showed you with all those numbers. First difference, second difference, you can infer everything. It's the same thing. So now we have our usual trick. M for the P branch is minus J, and for the R branch is J plus 1. Now we have M for the Q branch is J. So you can actually find, using this notation, you can find simple results for the energies. It's a constant, within a given vibrational band, a constant plus these are the rotational terms. The only parameters are A and B, and they're just always the combination. So if B prime and B double prime were the same, life would be good, but they're not. Because the minimum of the potential energy wells varies now more with internuclears, has different variable spacings. There'll be larger values, differences between B prime and B double prime that come into play. And there, we're back to here. So this is, once you have the parameters, you can plot. These are the positions of the lines. And now maybe you're getting ready to know 20,000 wave numbers is 500 nanometers. Get used to these numbers. So, and if you look close, you can explain why there's no lines here there's no lines right in here, because it has to do with the fact that you can't have J less than lambda. So there's some lines missing, but other than that, it's really pretty much what we've done before. Now, people have asked this question. So we got line positions, there's line strengths, and there's line shapes. So what about the strengths? In my simple world, all the lines have the same strength per molecule in that state. So in other words, the distributions in the P and the R are exactly the Boltzmann distribution. Well, it turns out they're not exactly the Boltzmann distribution because of the Hanson-London factor. And also the Hanson-London factor will help us explain the strengths of the lines in the Q branch. So now we have three places to be, P, Q, R. If you're in a given state and you undergo absorption, and you can have a P or a Q or R, what's the relative strength? And the Hanson-London factor is nothing more than the relative strengths of going to a P, Q, or R. So if it were perfect world and delta J was 0, there'd only be P and R, and they'd be equal. Well, they're not exactly equal, but they're close. So the Hanson-London factors represent the relative propensity between P, Q, and R as a function of J. It's a correction factor, but we need it. So that's the breakdown of my principle of equal probability. I don't think anybody, and no one else uses that. I like to use it because it explains, it's mostly about the Boltzmann distribution. Okay, now, if we had a symmetric top, which is the one we're talking about, and if we had, for the case where we have delta lambda of 0, remember the selection rules are slight, well, the Hanson-London factors are different for delta lambda of 0 and delta lambda of 1. If in the case where delta lambda is 0, here's the strength Hanson-London factor for the R and the Q and the P. And they look kind of complicated, so just imagine them in the limit of large J. It's J plus 1. 0 and J. So basically, in this case, this explains the fact that the R branch is J plus 1 over J is the weighting factor. They're defined, and this is takes a while to master this. The sum of these numbers is 2J plus 1. And it turns out that when you look at the relative propensity of going for P, Q, or R, it's really what counts is this number divided by the total. So it's the fraction. So the probability of going for an R is j plus 1 over 2j plus 1. Probability for the P is j over 2j plus 1. So it's really just relative probabilities. If you're in a given j and you're going up in a given delta V, and you just want to know P versus R, my principle says that they be equal. London says no, they're not quite equal. The ratio is j plus 1 over j, more likely in the R than the P. So that explains everything. The London factor explains the questions that I've been getting. Now, if you have delta lambda of, okay, here I'm saying it for you. The R branch for specific j is j plus 1 over j times the strongest as the P. In a perfect world, that ratio would have been 1, but it's not quite perfect. Now, if I go to the selection rules, London factors for delta lambda plus or minus 1, remember, delta lambda can be 0 or plus or minus 1. And what does that mean? You're actually going to different states, and therefore they have different wavelengths. In this case, interestingly enough, in the limit of large j, is 2j plus 1 over 4. So in other words, since I'm going to eventually divide by the sum, 1/4 goes here, 1/4 goes here. All of a sudden you realize the Q branch is twice as strong as the P and the R. So the London factor is the thing that tells us the relative propensities for P, Q, and R. And it's relative. It's not an absolute number, it's a fraction. Okay. Now, here's some examples. Here's some symmetric top-ground states. Okay, so now what am I looking at? I'm looking at, well, I could be, okay, I use the arrow now to tell you that because there's confusion between upper and lower, atoms do it one way and molecules mostly do it the other way. I'm going between a ground 1 pi state to an upper, what does that mean? Delta lambda 0. But I can also have delta lambda of 1, or I can have delta lambda of minus 1, if in this case. So these are the electronic term symbols for the 3 possible delta lambdas. You're going to a different place. And then within that place, you have P, Q, and R. And within that place, you have Frank-Condon factors. So it's like molecules now in rho vibronic spectra have lots of options. You're in a specific state, identified by all its quantum numbers, and you can go a lot of places. And so the Frank-Condon factor tells you the relative propensity for specific change in V. The London factor tells me the specific propensity for J. And for within a given electronic change, a given delta lambda. Okay, that's a lot of stuff. Now we add spin. So what does that mean? We need to now have to worry about the component of the spin in this direction. So if there's a component of lambda, this is the case where we have, there's two Hans cases. One's where lambda is unequal to 0. That's this case here. One case where lambda is 0. So because lambda is 0, the spin doesn't quite know what to do. And so it's different. So S hat now is a vector not locked to this unique axis. So now J is the sum of N. N is the nuclear masses, and S. So what we have, these are vector diagrams. It's just a question of what is the vector diagram. So in the case where you have orbital angular momentum, you do this, and that's why we have an omega. Now there's always complexities. There's more complexities. I almost hesitate to tell you about this. So it turns out it makes a difference. Imagine this is nitric oxide, NO. Well, it turns out that lambda can either point one way or point the other. Almost the same, but it's slightly different. And so, in fact, because you're in a given quantum state now, you may have another choice. And that choice causes a doubling of lines. So what we're going to find is that the spectrum has got lots of choices. lots of lines, and that complicates our ability to calculate. Okay, now we're back to the term symbol. And all of this stuff is in your notes, so you can at least carry it away. The term symbol, the complete term symbol, it tells the spectroscopist everything you kind of need to know about the state. It gives you the spin, the orbital angular momentum, and omega when it's defined. Omega is lambda plus s. So this is the projection of electron angular momentum when there's both orbital and spin. So the spectroscopic accountants have given labels to everything, so you keep track of everything. And this, in the end, then means we have 4 models. It all has to do with the values of lambda and s. If they're 0, life is good. A little bit more complicated. It's just a symmetric top. You've at least seen it. A minus b squared, lambda squared. Hans case A, Hans case B. So these are models, the 4 different models, which correspond roughly to molecules that we know about: nitrogen, hydrogen, OH, NO, O2. So our molecules that we care about usually fall into one of these 4 classes. Turns out that when you have, especially when you have an H, because it's so light, it kind of throws things off. And so we'll find with OH, which is an important species, that it's a little more complicated, and we end up with something called an intermediate model. Okay, molecules, to review, we're adding in electrons. They have orbital and they have spin. Whereas right now we're neglecting nuclear spin. We're imagining we have an asymmetric molecule. It's just a vector diagram subject to the rules of quantum mechanics that vectors can only have certain components. So it's a vector, but it can only have certain components. And by the way, that's why in the end, a state has a residual degeneracy of 2J plus 1. If you're in an energy level, that's the number of states in the level. There'll be a degeneracy there. But if you reduce it down to a state, because the quantum rules are between state to state, there's a residual 2J plus 1. Why? That's because if there was a field, it would only be, there's 2J plus 1 allowed orientations. But we don't have a field, but we still have to keep track of this. It's like the symmetry factor, and you have to, how many ways does it look the same? So quantum mechanics is a lot about symmetry factors. So there's this problem that if lambda points the other way, there's a slight difference in the energies. Spin, we have to sum L and S. Okay, so if you have an even number of electrons, you're going to have an integral spin. An odd number, you're going to have a half integral. Lambda is equal to 0. That's just that's the symmetric top. It's precessing around. So there's always a mechanical model for these things that you can appeal to if you need to. Okay, total angular momentum. If there's a component of lambda and sigma, we have to do this. We add them up to get omega. Okay, let's see. Sometimes it's nice to have kind of a physical definition of what's going on with these in the influence of the field. So if lambda is equals 0, that means the electrons are orbiting around. That electron current kind of produces an effective magnetic field along the axis of the molecule. So it's kind of like the electron current implies a magnetic field current. And there's therefore an interaction that you might think about in terms of electromagnetic theory, that the interaction energy associated with that momentum and current is the energy contribution is given by a multiple of mu as a factor for. Do one case where we actually, this is all the things you have to do to know what you're doing if you're measuring OH. And there's just a lot of stuff, but you won't master it in one go-round. But therefore, you should just take away a little bit of information from this. presentation. So we're going to do absorption transitions for OH. And now what have we learned? We've learned that OH, and this would be in the X 2 pi to A 2 sigma transition. That's the strongest OH transition. Strongest electronic transition. And it's about 300 nanometers of light in the ultraviolet. And so I'm going to just hit the high points. So if you want to find a state, you've got to tell me N and J, and you've got to tell me, this is lambda doubling here. So basically, N of 13 has two values of J. J is N plus a half and N minus a half. That's the spin splitting. So given N has two J's, 12 and a half and 13 and a half. And that so-called, the label beta is when I'm saying F1 and F2. F1 is J equals N plus a half. F2 is J equals N minus a half. So for a given N, okay, for a given N, there's two J's. This is the J equals N plus a half. And that's we use the label 1. And then there's two orientations for lambda, one direction or the other. That's the lambda doubling effect, which is small, but it's there. Why do I care? Because I've actually taken those molecules and I have to decide which quantum state they're in. So in fact, when you think about it, for a given N, there are 4 states. And absorption takes place from a state. And the statistics apply to a state. Once I get to a state, the remaining degeneracy is just 2J plus 1. That's this magnetic field thing. If I just say, well, I've got N of 13, well, now I've got to recognize there's this degeneracy, there's 4 right away. So if I want to, and these are the allowed transitions here in their notation. So there's the beta of 2, that's J equals N minus a half. Okay, and they have certain rules. So here's the relevant quantum states. The upper state, that would be the A state. It happens to be a sigma state, not a pi state. So, and now we apply our rules of delta J plus or minus 1 and 0. And so it turns out that you can go from all of these now, these are J's and minus a half. I shouldn't be looking on this side. The J's are always N plus a half on this side. You can go between F1 and F2, but these are weak. So these are supposed to be seen as very faint lines. They're called satellite branches. So what's the bottom line? The bottom line is if you're in a specific state, meaning that I know beta and I know J and N, and I know that I'm a C, I can only go 2 places, R2 and P2. So the 2 here is this 2 here. But I also have a Q. So there's 3 possibilities, but the Q only takes place from D. So where does all that come from? That comes from something called parity. So there's parity is a wave function symmetry property associated with these states, and the quantum rules have to do with you have to maintain parity. You have to go from a C. You have to change parity. You have to go from a plus to a minus. So these are just the selection rules. They're known. They're numbers. So the point is, the Boltzmann distribution is not enough. Not enough to know the fractional population in a given J. You got to recognize that it's carved into 4 options. Therefore, you've just lost factor 4 in your detection sensitivity. So all of this is about how you figure all this stuff out and apply the selection rules. And I'm going to kind of zing through it because what I want to do today is something I haven't done before. These are 2 case studies. Usually I spend time on this ultraviolet case. I want to introduce what we're starting to do with hydrocarbon fuels as a case study. So I'm going to zing through this a little bit fast. You've seen this before. This is a plot of the line strengths at a specific temperature for the transitions in this band. This is the zero. This means I'm going from V double prime of 0 to V prime of 0. There's the V's. There's the electronic change. And now it's all about rotational. It's all about rotational analysis. And so what do you see? You see that, well, there's something up here. Interesting. The Q branch is twice as strong as the R branch. Why? Well, that's from these Ronald factors. It's not always the case, but it is the case for this molecule. There's a Q1, that's F1, that's J equals N plus a half. Q2, that's the J equals N minus a half options. And the R's, R1, R2, so there's a subscript 1 and 2 corresponding to the F1 and F2. And then there's the Q that corresponds to delta J is 0. But you can see right away how this curve varies with, as I go across here, I'm really just varying J or N. And at this temperature, this one here, which is probably Q19, is the strongest. If I did this at a different temperature, I get a different Boltzmann distribution, and I get a slightly different optimum. So the strange story is that for 25 years or more, my group, we always used this wavelength right here, this band head, because there were two lines close together, and we could scan our lasers, and we could get temperature, and that's what we did. And I forgot the fact that actually we wanted more detection sensitivity. I really should be right at this wavelength. That picks up a factor of 2. So anyway, you may be constrained by your laser source, but you need to understand the influence of these Hanson factors to optimize things. Okay, so there are there's 7 steps to get to the absorption coefficient, which I lay out for you. You have to calculate the energy levels. Remember, the spectrum is all about differences between allowed states of the molecule. So you have to have expressions for the energies, take the allowed differences, and you have the spectrum, positions. The hard work is the line positions. The line strength is not that hard. The line shape is not that hard. So we identify we establish the allowed transitions. We make use of our notation, which is the accountant's way of keeping track of things. We impose the Hanson factors, which vary with the type of electronic transition. Calculate the Boltzmann fraction, calculate the line shape function, get the absorption coefficient. Okay, so you start with something simple. Here's the ground state. Look these numbers up in Hertzberg. Electronic energy 0, omega E, omega XE. Excited state, we have these numbers. So if you're just deciding you're going to do OH, it's been done for 50 years. You just have to understand the literature that already exists. So electronic transition energy is 0. There's a number and a number. The vibrational terms are easy. I just need omega E and omega XE. All the work is in the rotational analysis. And all the confusion is in the rotational analysis. Now, we have to decide what model to use. So we have to look at the upper state. We have to look at the interpretation of the upper state and the lower state to decide which case we're in. If you looked at the upper state, that's this one here, A2 sigma, that lambda is 0, that's the Hund's case B. You got spin, but no orbital angular momentum. On the other hand, I come to this state here, and I have spin and orbital angular momentum. What does that mean? That means if I look at the energy level structure of the upper state, it's a little different than the energy level structure of the ground state. And then I impose the selection rules to go between state to state. So you have to consider both states. This is the case where spin is uncoupled. That means you have to keep track of the fact that J is N plus, in this case it's N plus S and N minus S. So that would be N plus and minus a half. So we have F1, J is n. You only have to remember one of these. I always remember F1 is J equals n plus. And the others follow. So that just means that I have energy expressions for the two cases, F1 and F2. And these look, forget the D terms. Here's the spin splitting right here. So that's the spin splitting that we got into when we had that simple expression of the spin splitting is A equals A lambda sigma. So this allows me to calculate for these different states. So I've got a given, for a given J, I've got F1 and F2, or for a given N, I've got two J's. So it's not enough to tell me N, you also have to tell me which one I am. And they have different parity, and this, you just have to accept it. It's given to you. So we're almost there, except we have to worry about lambda doubling. Let's get, now we do the, you have to do this for the upper state and the lower state. I want to warn you that the rules, the modeling capabilities for these cases breaks down most for hydrides. Anytime you have a light atom on the end, H, rules don't work as well as they do when it's heavier. So it turns out that the OH behaves like a Hund's case A at low n and Hund's case B at large n. And so the models, the equations that people use are called the intermediate models. But they're known, they're in the literature. So if you tell me n, I have my expression for F1. Notice here there's a y, so when y appears, that's A over B. So we have energy level expressions. And this is just an interpretation, so this is in your notes. So what we have is, for a given n, there's two values of j. So what we're doing is we're moving from one quantum number, n, to recognize that there's two states. There's two different values of n. And then we have to worry about the lambda doubling. So you're going to go from 1 to 4. 1n can divide into 4 states. And that will appear in the Boltzmann fractions. These spin splittings are here. I won't spend much time on this. So if you really care about this stuff, you'll work through each one of these slides, and you'll see if you can follow the material. Now I put in lambda doubling. So all of a sudden, 1n goes to 4 states. That mostly just affects the Boltzmann fraction. But there are 4 states with n, which means if you had a rigid rotor and I gave you n, you could calculate the Boltzmann fraction. And so in the end, don't get confused by this. If I took the rigid rotor number, divide by 4, I've got it. It looks like a lot of density, but in fact, in the end, it's just a factor of 4 that's floating around in this thing. Now, this is all to do with the ground state. I also have to pay attention to the excited state. Now, remember, we have this notation that I introduced for you. And now, this is called the full description. So this right here is the full descriptor of the transitions between a state to a state. So in many cases it simplifies, but this is the full descriptor. There's a superscript, primary symbol, double superscript, and then inside of brackets will be n or j. Remember, j is n plus a half, or n minus a half. So if you see in here a number, it must be n. If you see in here a half integer, it's j. So that's what's shown here. And x is now the, y is telling me something, which I think it explained here. This table will show you everything you need to know about the symbolism. I'm not going to go through it. Frequently, the strongest transitions are ones in which y, where delta n equals delta j, and so it gets more compressed So you have the rules here. Here's an important rule. Parity must change. So if you're given the parity, the upper state has to have a different parity. All that means is all the possible changes are reduced down to a finite number. Okay, so we're back to this diagram. So in fact, you now can interpret this diagram. Here's a given n. There's two possible j's. J is n minus a half, so this is a 2. There's a lambda doubling. C and D simply represent the two lambda double states. By convention, C is always the one higher than D. These transitions between these branches are minimum. They tend to be weak. Where will this show up? You'll see it in the Ronald factors. Okay, allowed transitions. So if you're looking for the transitions between a given n and upper states, there would be 12 possible transitions. But forget the ones in the middle. There's 3 strong ones from each of the betas. Beta 2, and so mostly the beta stays constant. And now, what's the relative propensity for P, Q, and R? So what you'll do is you go back, if you care about this, you'll go back and you'll try to understand from a given state, what are the possibilities? And you find out, well, these are the only possibilities. And if you obey the parity rules. Okay, now, the Boltzmann fraction. Simple interpretation is, tell me n. Calculate the Boltzmann fraction, rigid rotor, divide by 4. But a lot of this is explaining why it's the exact factor of 4. So the absorption coefficient, a number density in the state, the oscillator strength for the specific transition, state to state. The term is approximately 1 in the line shape function. Everything is buried right in here. To evaluate, to get the absorption coefficient, I just need the oscillator strength and this Boltzmann fraction. So if I write this number density as the absolute density of that species and the Boltzmann fraction, I do that because what I'm really interested in the end is this number density of that species. All of the work is in the oscillator strength and this fraction. And it'll look kind of dense, but when in the end, one of them is just a 4. This is a reminder that to get the oscillator strength for a specific quantum transition, I really need to specify all the quantum numbers of the state. But it's usually simplified down to the electronic probability, the Frank-Condon factor, and the Ronald factor, the normalized Ronald factor. So maybe it's easiest to think about in the context of emission. You're in a given state. You're allowed to emit to several lower states. The sum of all the A coefficients is the electronic oscillator strength. The fraction of those that go between a specific V and another V is the Frank-Condon fraction. And the fraction that go from a specific state to another specific rotational state is the Ronald factor. So it's really, the overall strength is determined by the combination of those 3 things. And so if you keep that interpretation in mind, it's not as bad as it seems. Now, you'd like to think that the oscillator strength is well known. Turns out that the oscillator strength, now this would be F00. So F00 would mean I'm talking about the transition probability between specific V's. So F00 means the oscillator strength for going from 0 to 0. And over time, people started measuring this back around 1938. And they got a number which is amazingly good. 3 zeros, 9.5. But over time, people got strangely different answers. That one there. But the bottom line is that the initial guy, I think, got the very best answer. And it all boils down to how did they do this? How did they measure these things? So there's more than one way to do it, and people got more than one answer. So the oscillator strength is not a, it's probably known for OH, it's probably known to 2% maybe on London factors. So I give you these tables and you could try to figure them out. So over here, so these are the Honnold-London factors for specific transitions. So let's look, P1 here, what does this mean? Remember, this means J is n plus, the 1 tells me that J is n plus a half. The P tells me that delta J is minus 1. 3.5 tells me that I'm talking about J, not N. So that means that N is 3. And here's the Honnold-London factor normalized by 2J plus 1. So the sum of all the transitions with 3.5 has to be 4. Because there's 4, that's the 4 that comes out to play. So basically, and there's 2 in the F1 and 2 in the F2. So these are all the, this is the notation for all the allowed transitions for J of 9.5. Remember, J can have 2 different values of N. You can have 2 different values of lambda doubling. So you have to keep track of all these possibilities. And, but in the end, they have to sum the fractional population, the fractions, Honnold-London factors have to sum to the right number. Now, this is going to be a lengthy path to explain how you do the Boltzmann fraction, but when you're in the end, I'm going to show you it's actually pretty simple. So remember, the Boltzmann fraction is given by the population, the expression that we've seen many times. If you're in electronic, you have to decide now where you're putting the energies. The electronic, there's the vibrational, there's the rotational. But the rotational leads to some splittings that sometimes are subsumed into the electronic. So the electronic, I went too fast here. Okay. So I'm going to evaluate the vibrational fraction is simple. We already have done that before. That's simple. It's the rotational mode that's the killer. So here now we have the rotational mode. The Boltzmann fraction would be, when we first part of the course, it was 2J plus 1. It's now 2N plus 1, because when we bring in the electrons, we have to change notation to use N for the nuclei. So this is the rotational distribution for N. But remember, it's not enough to tell me N. You have to tell me which C or D, and you have to tell me F1 or F2. So basically, we fight through all this in the notes, and you end up with, well, this fraction this fraction here is 1/2 because I have to recognize there's 2 values of N. And then I have to worry about the C and D, and I get another factor, which is 1/2. So when we're all through, I can actually write down the expression for the fraction in the quantum state, the fraction in the quantum state that's absorbing or emitting. But if you look at it, it's really there's the recognizable vibrational term, the recognizable electronic term. It's this rotational term that's tricky. But in the end, I'm just evaluating Boltzmann fractions. And when I'm done, and I'll go through an example for you here. Okay, measured quantity. Remember now, okay, so we're doing an experiment. We measure the fractional transmission. It's governed by K nu L. And here's the line strength. I got line strength, line shape, path length. And I just have to, it's all here. This is where all the work goes. So you measure the fractional transmission, you know the path length, you know the pressure, you know 2 gammas, you know the oscillator strength, you know the temperature, and you can evaluate everything. So here's an example that I worked through at 2000 Kelvin. Picked a transition here now that's the center. Okay, here's the Q1 line. So I'm recognizing the Q1 line is probably the strongest line in the 0, 0 band. I can calculate K. All the work goes into these 3 pieces right here. The line shape is 2. You know how to do that. The work that goes into 1 and 3. I look up the oscillator strength in a table and Honnold-London factor, do the line shapes. Now, I have to put in the partition, I have to put in the Boltzmann fraction. Step 3. This is the one where there's a lot of terms, but when you're all through, there's just a simple 1/4 here, which is the splitting. So a given J goes to 4 possible N and lambda double cases. So if you recognize that, it's really just the vibrational contribution in level 0. So at this temperature, vibrational population is dominantly in B equals 0. And then this is the rotational term. So this says that 8% of the molecules have a specific J, although only 1/4 of those are in a given quantum state. I think if you keep this in mind, you can always kind of make sure that you've got about the right answer. What did that say? I should go back. In the end, let's see. Okay, so when I'm all done, what is this? That says that the Boltzmann fraction in the absorbing state is 2%. Not bad. Not bad. 2% are in that state. Okay, so now I can convert this to an absorption coefficient, calculate it for a given path length and pressure and so on. I get a number of 177. And I apply this to Beer's law, and let's assume I have 59% absorption, 41% transmission. Assume a path length of 5 centimeters, assume a mole fraction of 1,000 ppm, that'd be 0.1%, temperature of 2,000 degrees. And so, I didn't do that right. I didn't say that right. If I have Beer's law, and if I had 1,000 ppm at these conditions, I would get 59% absorption. Or if I measure 59% absorption, I can infer 1,000 ppm. So what does that tell you? I get a lot of absorption on this transition. If I do this at 1 atmosphere, 2,000 Kelvin, path length of 5 centimeters, I get an easily measurable signal. So it's very accurate. So we go to all this trouble to measure OH accurately. You might say, well, why don't you do OH in the infrared? It'd be easier, but the signal would be 0 because the oscillator strength of that OH transition in the infrared is down by 3 orders of magnitude. So if you got plenty of CO, CO2, or you're doing HCN, you use the infrared, simpler. So this is basically, this lecture is all about where did I get this diagram? How do I pick the transition I want to use? So, and this diagram changes with temperature. Okay, I wanted to spend some time on something new for this lecture, and also new for what I'm doing in my research program. We have a lot of interest in aircraft fuels, sustainable aircraft fuels. These fuels are coming along, and there's questions about their properties, combustion properties, physical properties. And so we have this one goal to find a compact spectroscopic way of looking at the spectrum of a fuel in the infrared and telling you from that spectrum what is the fuel, what are its properties. And I'd argue that if we, because these are hydrocarbons, and the hydrocarbons have infrared spectra, it depends upon the structure of the fuel, that if I have a good enough measurement of the spectrum, I can use machine learning to tell you what the composition is, or at least what the primary components are. And I can tell you about the functional groups that are important, and therefore, in principle, I can go from the spectrum, look at the spectrum, and I can of the fuel vapor, and I can tell you the density, the viscosity. I can tell you everything. Why? Because the structure of the molecules in this fuel determine everything. What is there other than the structure of the molecule? There's some subtleties if you get into some liquid situations, but nonetheless, that's my idea. And so the goal is to that we're working on this. We've hardly published anything on it yet. Is to develop a compact, low, and we only need less than a milliliter. A little bit of liquid, because remember, the volume of the gas is going to be 1,000 times bigger than the volume of liquid. So if we do this at atmospheric conditions. So we take a little bit of liquid, put it into a vessel, measure the spectrum, and hopefully, by and that by correlations with enough of a library of trained results, we can give you the answer. So that's my idea that motivates what I'm going to try to show you. So how do we get the spectrum? We'd use a Fourier transform infrared device, FTIR it's called, and we'll measure the spectrum, and we know from our early lectures, the CH stretch, which appears all along the structure of the hydrocarbon molecule, occurs at around 3 microns, 3.4 microns. So if we were to look at here's two fuels. Let's see, what do I got here? I got Jet A. Jet A is the pink one. So Jet A is a composite. The green one is CH. The green one is CH3. So imagine, say, heptane. It has two methyl groups, one on each end. In between, along this chain, there's some CH stretches. So your spectrum is going to reflect all of, now remember, 3n minus 6? That's how many vibrational modes there are. But they fall into categories that people have given names to. They'll call them the CH3 symmetric stretch, CH3 asymmetric stretch, and there's words like twist and waggles and rocks, and there's different words given to the motions of the carbon and the hydrogens that can be associated with particular spectral locations. So the idea is, this is just of the 3 micron, the idea is that clearly you see completely different spectra for these 3 different fuels. And so you might be able to say something about the composition from the shape and the height. Okay, if I make the fuel molecule bigger, meaning more C and H's, there's more places to absorb light, and the spectrum gets higher. So this is a combination of this is the cross section for absorption, which gets higher as I increase the number of CH motions, the size of the molecule. So the size of the molecule is shown up here, and also the relative propensity to be, say, to have a methyl group or a CH stretch along the spine of the molecule. That's the concept. So this is another kind of spectroscopy. This is like, we talked about discrete small molecules. Now we're talking about big molecules. We don't talk about quantum states anymore. We talk about functional groups. And so, for example, if we had N-heptane, it looks like this, with methyls on the end. Here's the isotopes. We could have isomers. We could have methyls here. So it depends on the degree of so-called branching. If you change the amount of branching, you change the proportion of the CH3 motions compared to the CH2 motions. So we give these things names. It turns out the major places to look are around 3 microns, 7 to 8 microns, and out around 11 to 12. If you go way out here, you get some vibrations that have to do with the stretching between the carbons. Remember, we got 3n minus 5. We got a lot of things going on here. And here's the rocking. So that has to do with particular motions of the CH2 groups. They're given names. So we go from 3n minus 6 to, we categorize them into groups, and they appear in different places in the spectrum. So you begin to see that, gee, if this is a case where I'm looking at the 3 different isomers. These 3 different isomers look quite completely different out here. In here, it might be a little harder to discern, but anyway, depending on the question, maybe the question is, can I discern the differences between these 3 forms of C7 in my blend of fuel? The answer is yes. So if you have a library of these characteristics, you might be able to look at a sample of fuel vapor and infer from the spectra the primary species and structures. And it turns out that xylene is a particular structure. It's a closed ring with 2 methyls. And for reasons I don't fully understand, this is an important one for characterizing jet fuel. And if you had samples of these individual molecules, they would have completely different boiling points and physical characteristics. And it turns out if you're worrying about the behavior, then if you want to characterize a jet fuel for its propensity, for its density, or for its boiling point, or if it's ignition delay time, you might care about the relative amounts of these isomers. And so you have to have a method which could look at the fuel vapor and discern the proportions of these things. And so my friends who use gas chromatography, which is the competing methodology, are having trouble with this particular problem. My guess is that there are some things that will be, some issues, some properties, some physical properties, we might be able to measure better than are with better correlations than by GC and vice versa. There's probably, no method is perfect. So this is these are just names. So these are called the CH-WAG and so on. But here's a place where we might have trouble discerning these three here. There's some difference here possible. This looks like if we had a sample of these three, we could say how much we have of each one. So these are the spectra of the individual isomers. But you have to imagine you have a sample that has all three, and you look at that and you'd infer, well, how much of each one? So that's the concept. And some of these properties, like this freezing point apparently is a really important one for the performance of the sustainable, SAF stands for Sustainable Aircraft Fuel, the fuels are coming along. The property, so the people who are trying to make these things, they have to worry about how you make it. But in order to satisfy the FAA that you could fly it on an airplane, the flight test or the ground test of an engine consumes hundreds of gallons. The people making this stuff are making, milliliters playing around. So there's a real need, we think, for a fast, low volume concept for characterizing the anticipated performance of this as a fuel. That's the idea. Okay, now this leads me to something that I call, when am I supposed to end here? I'm supposed to end at, maybe I'm ahead of schedule. Okay, so this is the concept here, kind of in schematic form, that we can take the spectrum, which after all, think about it, if all of the functional groups have a spectra, and if you measure the total spectrum, in principle, if you have high enough quality data, you could say something about the composition and the functional groups. So you might correlate it immediately. So if you took the, you have a training set in which you have the spectrum and you relate it to physical properties, say density or boiling point. In principle, there's a unique relationship if you can unfold the spectrum. So you can do this a lot of different ways. You might go immediately from the spectrum to the properties. But we also have a method where we go from the spectrum to say, what are the functional groups? Or what is the composition? So we will sometimes ask, can we go from the spectrum to the composition, the primary hydrocarbon in the mixture, in the mixture? Or can we tell you about the functional groups? Because from the functional groups, you can predict kinetic behavior. So there's like three options. You go from the spectrum through these intermediate steps, or you might, so if I know the composition, now I got to be able to correlate it too. What's new for us is to ask a new question. Can we go directly to some combustion properties, like ignition delay, derived cetane number, flame speed? And so we already think we know how to do it by, if we go through the functional groups, we got to be able to predict the kinetic behavior. So we want to build, say, a detailed kinetic model. And could you go from the spectrum? Because remember, the spectrum actually reveals the structure of all the molecules. Some are more important than others, but so in principle, the chemistry is buried there. Could you go from that spectrum to predict the kinetic model, which is comprised of tens or hundreds or thousands of chemical reactions? That would be a dream. So we're working on it. I'm going to show you how well this idea works. At least we've been working on this a couple of years. Here's molecular weight. If we looked, if we have some sort of a limited training set, so we take some neat hydrocarbons, fixed molecular properties, and we know their molecular weight, and we measure the spectrum. So we have to have some sort of a training set. Then you could take the unknown, and you can compare it with the known. But one question is, how well can we fit the data for use some sort of linear regression model? How well can we fit the data between the actual molecular weight and the inferred value from the spectrum? If we limit ourselves to the 3 micron region, it does not too bad. But if we use the entire 2 to 15 micron region, which is what we've been doing for the last 2 years, I had a student who was very clever. We were measuring the spectrum. We were measuring the amount of fuel in our shock tube by using the cross-section. And he observed that if we measured it at 2 different wavelengths, that ratio, not only could we use either wavelength for the amount of fuel, the ratio predicted the ignition delay time. That was the first time we realized we could learn something by looking at the spectrum. In any case, then we decided, well, he used only 3 microns. So the new student uses 2 to 15. And so if we use the entire knowledge that we measure from 2 to 15, this is getting pretty good. This is the molecular weight. And so how well it fits is indicated over here by these performance parameters. R-squared number means it works pretty well. So in other words, they fit on this line. That's a good sign. And we can do the same thing for the boiling point. So basically what we're learning is that if we're willing to use the entire spectrum from 2 to 15 microns, here's our category. So we have a training set that we keep getting bigger and bigger. So we have some known in paraffins, isoparaffins, cycloparaffins, and then we have some real fuels, and for which we know the properties. And we measure the spectrum. So it's a measure of how well are we going to be able to predict these parameters. Okay, I'm losing track of when I'm supposed to be. Am I supposed to be done now, or, well, supposed to be done at 11? Maybe I'm ahead of schedule. So what I tried to show you in this last example is that when you go to the infrared, you don't talk about line shapes anymore. You talk about cross sections. And we're still talking about the spectrum, but now we're talking about the infrared spectra of hydrocarbons, not the electronic spectrum, infrared spectrum. And the spectrum is related to the structure. And the structure determines the performance of it determines everything. There's only the structure of the molecules that come into play. All right, so I tried to give you this is new to my lecture, show you the infrared, the power of spectroscopy to do practical things. This is kind of a connection to machine learning, which is very much in vogue these days. Okay, so I'll take some questions. Let's see, I think we have some time. Take some questions of any kind. Yeah. Yeah. So let's see if I went back to a few slides here. Let's see if we'll go back. What do I want to show you? Okay. Okay. So if you look at this on the left, we had been measuring the hydrocarbons at 3.39 microns because helium neon lasers emit at 3.39 microns. And people have known this forever. So they've been around 50 years. So it's easy to measure hydrocarbons. You just take a helium neon laser, 3.39, and it's proportional to as a cross-section for the fuel. Okay. Then the laser started giving us trouble, so we thought, we'll buy a new one. This may be better. So we decided, well, let's buy one 3.41 because it looks like we're going to get stronger signals there for some representative. We did the FDR spectrum, and we saw, gee, we get stronger signals at 3.41 than 3.39. Let's use that diode laser. Then we started noticing, the student was clever. He noticed that why he did this, I don't even know. He said, if I looked at the ratio, it really correlates with ignition delay time. And that was because he was measuring this CH2. So in a sense, he was measuring the relative proportions of CH3 and CH2. So basically, the ignition delay time depends upon the structure. ignition delay time depends on the structure. And we were probing two different parts of the structure. And so just got lucky. The ratio was really a good indicator. It wasn't, then we said, well, we do two wavelengths. Why don't we use the whole spectrum? So then we started using all of this region. And then we realized, well, why aren't we using the entire region, 2 to 15? So basically, we got lucky that when we were, because we bought one, and I had a sample of the spectrum of the jet fuel we wanted to measure. And I said, gee, it absorbs really strongly at 3.41. Let's buy our diode laser there. The 339 it's a little bit buried in here. It's a little hard for me to explain to you, but it turns out that the 339 is kind of a measure of the total amount of hydrogen. Whereas the 341 is kind of a measure of this asymmetric stretch. It's kind of a proportion of the reactive group. So it was pretty sensitive to ignition delay. But once you realize, well, if it does ignition delay, I mean, if we use the entire spectrum, it'll get even better and better. So it's basically recognizing if you map the spectrum, you have mapped the structure of the fuel molecules in the mixture. If it's a single molecule, it's kind of simple to interpret. If it's a blend, however, now we got to worry about the superposition. But in principle, if you use machine learning and you have this, if you accurately measure the full spectrum, and if every hydrocarbon species has its own spectrum, you can say how much each you have to some accuracy. So it makes a lot of sense. It took me a while to accept that we could get boiling point, ignition, we could get everything from this, because the structure determines everything. If you have methane, heptane, whatever it is, those two things, they burn differently. But they burn in a way that's related to their structure. So once you fix the structure of the molecule, you effectively have to fix the chemical mechanism that describes what happens when it combusts. So I think it took me a while to accept that the magnitude of the spectrum is reflecting the total number of CH bonds. And you look at the shape, and pretty soon you can get the CH ratio, and you can kind of get everything. It's kind of easy to imagine if you have a single hydrocarbon. It's a little harder to imagine. So once you fix the structure of methane, all the properties are known. Somebody's measured them. All the properties of methane are known. Okay, so now you put in methane and ethane. Still, if I measure the spectrum, I can say, well, how much of each do I have? And then I can at least correlate it with the properties that are measured. So it's kind of, I think the GC people who are my competitors would probably have a different argument, but the point is spectroscopy is about the structure of the molecules. And the structure determines all the behaviors. Boiling point, density, viscosity. It took me a while to figure, surface tension even correlates. Yeah, question? Well, so this was we're pursuing multiple, this one here. So we have different strategies. We call them strategy 1, 2, 3, 4. So we'll use strategy 1 is kind of, we immediately go to the answer. I think it's strategy 2, we go to function. So we have different ways. So basically you have to have libraries of spectra. And that's a problem because you don't always have a measured spectrum. So maybe it's some rare isomer. We have to either find the spectrum and the physical properties, or we have to measure. So, but sometimes we'll ask the question, well, what's the composition? I mean, after all, the spectrum is the sum of the individual compositions. We do this in vapor form, by the way. So I had this idea, and I had a friend at Shell. Shell, Shell, you should pay attention to this idea. I think we could, a couple of wavelengths, we could probably tell you the octane number for you. And I think this is interesting. So he said, okay, he checked with his expert, and he said, nice idea, Professor Hanson, but we've been doing this for 25 years. So it turns out that they would use near infrared. They would use a couple of wavelengths in the near infrared of the liquid, not the vapor. And they use this to correlate with octane number in the refiner. So it's used in industry. They just don't talk about it a lot. So, but then I thought, well, that's kind of disappointing. But we do the vapor, which means that the spectrum is easier to resolve, better resolution. We use vapor, and we use all the wavelengths. I don't think they do this. But there are companies now, we're beginning to find little companies that are kind of selling devices that will measure the spectrum and give you some properties. But I would think that they're not into it as deep as we are. We're trying to really understand this and optimize it. But it's, yeah, it works, and it can be used for, so you can, now the thing is, if it's a mixture of, say, 5 things, you probably can do this. The higher the accuracy of your data, the higher the accuracy of the database, the better you can do this. Assuming all 5 of them absorb to different degrees in different places. Of course, now once you get above 5, how many species can I infer? Well, that's a good question. I don't know. If in the limit of ultimate accuracy of the database and this measurement, you can do better and better and better. Can we detect a component present with a mole fraction of 1%? It's going to be harder. But if you tell me, I especially want to know this isomer, well, I'd zoom into my knowledge base and I'd say, the best place to look for that is right here. And you might be able to do it better. But that's a good question. How do you deal with complicated mixtures? That's the problem. But I think, maybe you don't have to know all, if there's 100 species, you don't have to know all 100. I can ask the question, how many of those species determine the boiling point? Can I measure those? How many of those species determine the ignition delay time? Can I measure those? So if you look at it that way, you probably don't have to know everything to get an engineering answer. Yeah.
Going back to why did your dynamical engine, they have the shortest carbon change, if you will?
One more.
Yeah, the dynamical engine have kind of the shortest carbon change, if you will.
Yeah. It has more methyls.
Why do they have the strongest skeletal vibration?
I don't think I've ever thought about it that way. I haven't paid much attention to that. Well, my guess is that, the magnitude of that strength of that stretch may vary with the length of this thing. So it's probably, maybe as simple as saying that, well, the overall length of this thing is shorter, maybe it's more compact, maybe the frequency that it takes to excite it is higher. I don't know. It's a good question, but I don't know the answer. I'm more looking at, can we at least see distinct differences in the spectrum? But now you're asking a good question. You could also ask, which of these motions is most important for boiling point? We're learning how to answer this question the other way around. I asked the student, well, if we're interested in the boiling point, what should we look for? That's kind of like the reverse of, if you measure the spectrum, what does it tell us best? Mostly this is like looking at these motions, and you can see as you change the degree of branching, so I'm looking over to the left, change the degree of branching, you can see the increase in the strength of all the things that say CH3, because there's more CH3s. And there's a lot of questions here. What is the CH3 symmetric vibration? Well, it's kind of like the H is kind of all being synchronous. But remember, there's a lot of modes here, 3 and -6. There's a lot of them. So you say, well, I can sort them into certain bins. I'm not an expert in this, I'm still learning. Yeah. Well, I think you could do it in the UV. So we use molecules. We use UV of some molecules for combustion monitoring. So, for example, if you're a planar relation fluorescence person in an engine, you might be interested in toluene or these pentanone, acetone. They each have different spectra. But, if you're interested in hydrocarbons, you're kind of immediately attracted to the infrared. Electronic spectra, these things would probably vary less with isomers than the infrared. You know, the infrared is known as the fingerprint region. So every molecule that has the infrared spectrum has a different spectrum. So it's called the fingerprint region. The infrared is the fingerprint region of spectroscopy. The reason. So if you happen to read, if you read instrument books or read magazines that advertise equipment, there'll always be a lot of stuff on infrared spectroscopy. There's books on infrared spectroscopy. And people, that's their life, the infrared spectroscopy. And so engineers or people who work on process control, they'll be able to look at a sample, a liquid sample of some kind, and answer the very same question: what's the composition of the sample? And they know where to look better than I do. I'm still learning, but it's a common, you know, there's big business in FTIR analysis of liquids usually. Medical people do it. It's kind of new. I think it's kind of new for combustion people to do it. Yeah.
Is this something you also use for evaluating high-chem mechanisms?
Yes. Yes, exactly. So, in fact, very good question. So, high-bit chemistry, was an idea born at Stanford, mostly by my colleague Professor Hai Wang, and he saw that we could, when we measure time histories of species in combustion, that they fit into a neat pattern of short time and long time reactions. And if you approximate the short time reactions with a small mechanism, and then use a detailed mechanism for the small molecules, you could actually predict kind of everything. In other words, you don't need 5,000 reactions to model combustion. You might be able to do it with 100. So it's hybrid chemistry. And he saw my thing, and so we wanted to validate this approach. And we did it by measuring. His model means you have to understand the products of the pyrolysis. Big molecules want to be small molecules. Big fuel molecules want to be small molecules, and it happens fast. And if you can understand the conversion from the fuel to the pyrolysis products, you have everything you need for a compact chemical model. And he saw my data, and we were doing it. And after a while, we were doing it. After a while, I realized, since I am beginning to understand the pyrolysis products predicted from my spectrum, I don't even need to make the measurements of the pyrolysis products anymore. I should be able to jump directly from the spectrum to the combustion. And that means, so I call this IR high-chem. We haven't published on it yet. So my goal is that we're going to have an IR high-chem. That if you have the infrared spectrum, I can tell you the kinetic model. That's somewhere in a couple of years in the future, probably. Yes. Yes. I think mostly it's just a shift. This is something I'm still learning, but what I showed you is sort of those three isomers. There's a shift. As you change the position of the methyl, you shift the overall behavior slightly. Are you looking here or next slide?
In the ring bending section,
Yes.
so these bendings are going to just disturb the entire stability of the entire bending ring, and it will feel like a normal, an open chain. So is that so like a closed chain will have the highest extra peaks and open chain?
Well, you're asking a question I've never even thought about. So what we're looking for mostly here is, can we see a distinction? So we're trying to look, where do you see a distinction? And we see, so looks like I don't know how to answer your question about the ring bending. Looks like the ring bending is not very important. Looks like it's only small contribution. Okay, so my answer, because I get this question, and I don't know that I'm not sure that I have a good answer, but you know, we know Dalton's law of partial pressures. If you think of the molecules as separate, moving around in space, not interacting with each other, and then if you think of that all of the molecules of the same structure being independent, not really being aware of the presence of the others, I think the spectra have to add. So I think the vapor spectra add. It's a little different question when you get into a liquid. In the liquid, I think the molecules are aware of each other and the spectrum is perturbed. So we only, I don't know, other people do this, we immediately go to the vapor. I think the vapor allows me to make this assumption, kind of like Dalton's law of partial pressures, that the vapor spectra have to add. And we do the same thing, by the way, you know, when you have multiple lines, we assume that we can sum the absorbances. There's times when it gets a little complicated. There's something called line mixing. You may not have encountered this yet, but there are situations which you have to kind of be careful. Usually they're high pressure situations. When you get to higher pressures, you have to be more aware of certain interactions that can take place. So if the density goes up and the molecules never are, you know, the idea of in kinetic theory is that the molecules are independent of each other most of the time, and they bang into each other and they go. You think of that as a short duration. But as you go up in density, that starts to break down. So whether it's the thermodynamic models or kinetic models, that's a new problem. That's a problem. It doesn't seem to apply very much. You know, the combustion, you go up in temperature, the density's going down, so you're helping yourself a little bit. So I think vapor spectra add okay. But if you do it in liquid, I think it probably begins to break down. It's fast. It's fast. You know, it depends on. We have a very old FTIR, and didn't cost $50,000. Bought it 15 years ago. We should use the same one. So the nice thing about looking at these spectra is because we don't talk about lines anymore, we don't actually need high resolution. We'll measure the spectrum and we might bend it into, say, 2,000 wavelengths. Then we put them back together again because we don't really. That's the students will tell me that's there's a tendency to overfit the data, they say. So you're better off bending it into, say, widths of certain wavelengths and keeping those. Then you get to decide which ones are the most important. And so we don't really need, to my surprise, we don't need a better FTIR. One problem is we like to get out to longer wavelengths. And so the black body rule that did I tell you about Wien's law? Maybe not. You know, if you have a black body, anybody know what Wien's law is? The peak of the black body distribution is 3,000 micron kelvins. So if you're at 3,000 degrees, the peak is at 1 micron. If you're at 300 degrees, like you are, peak's at 10 microns. So people use infrared cameras to watch people move around. So, but the radiation source, you have to have a source for the FTIR. It's a hot glow bar, silicon carbide. And so how hot can you get it? Well, the ones you buy are maybe 1,200 Kelvin or, you know. So the point is they're peaking at I want something that's brighter at 15 microns. And the only way, you know, it's just hard to do this. So they are very bright. The law, it rolls off. So the quality of the data out at long microns, it gets a little bit, so what we play, students are smart. So when we do an experiment, we'll scan the spectrum of the fuel. And we'll mix up, we'll have a chamber of certain length, L. We put in a certain partial pressure, measure the spectrum. The strengths are bigger at 3 microns. So we use a different mixture. So he's ready to do 10 microns, he puts in more. So remember, it's all about K nu L, or sigma L. So there's a way to get higher quality data at long wavelengths that we need. But in the end, you can only measure so well, and what's the influence of that uncertainty? That's what we work on. And then we might wish we had a better FTIR. It's a lot cheaper than most lasers. So what I'm trying to do in this is new to me. I'm trying to show that you don't always have to use a laser. You don't always have to do discrete molecules. Sometimes we have to worry about big molecules. And it's all spectroscopy, but you kind of change your strategy when you go to big molecules. We don't think about lines anymore. Think about cross sections. So if you go to the database like high transmission atmospheric model, it's been available in the literature for 50 years. They'll report the results as a cross section. Only you have to be careful. Does the cross section change with pressure? But if it's not pressure dependent, it's just a function of temperature, and it's sigma. Remember, e to the minus n sigma L. If you give me sigma and you give me L, I can measure n, and so on. So the spectroscopy gets actually a lot simpler when the molecules, in some ways, when the molecules get bigger. Any other questions? Well, we burned up our time again. We're supposed to be done, I think, by 12:15. It does bother me if people leave, or I'll zing on to the next lecture and be done. Those who want to leave can leave. I'll probably, you want a 5-minute break? Nobody, 5-minute break, okay, take your 5-minute break. I'll drink some water. So if you're interested in diode lasers, the next lecture is the one. This is one of my favorite lectures because this area of tunable diode laser absorption is one that I feel like I helped start. So I've been around a long time, and I started with lasers around 1972, somewhere in there. And one of the first things I did was try to measure species by tuning lasers and wavelength. And the lasers we had were in the infrared, and they were diode lasers, so we call this tunable diode laser absorption spectroscopy, TDLAS. And I was supported for a very long time by the Air Force. And when the fellow retired, we'd been there for a long time, he wanted some sense as to how much had been accomplished over the time that he had sponsored me. And so I put together a story about how lasers had evolved in ways that have affected the Air Force. So I'm going to give you a history of laser applications to aero propulsion, some fundamentals, some strategies, and basically talk about the trends. But I put together this story for my sponsor it took 35 years from the time I had the idea. We got the laser, we did tunable laser absorption spectroscopy. 35 years from the time it was used in flight. So research takes time. It was 20 years from the time people found that they could measure particle velocity, laser anemometry, about 20 years before it was done in a laboratory and it was a product. It takes time to go from a laboratory to a real device. So I guess I did this in 1977. My dream was, could I combine lasers and shock tubes? Could I take a tunable laser, scan it across an absorption line fast, and do this in a shock tube? And that was my dream. I did that around when I was a research engineer, I guess, at that time. And so, jumping kind of major in time, 1977, the lasers were expensive, complicated. By 1989 or so, lasers were cheap. The telecom industry had gone into a boom, and there was some accidental coincidences between available lasers for telecom and the absorption spectrum of oxygen. So my idea was, well, why don't we use a diode laser to measure oxygen? And if we can measure velocity simultaneously in air, we can measure the flux of air into an engine. And later we did a thrust at the exit by momentum. But anyway, we started in the laboratory. We eventually went to hypersonic tunnel in New York. We started doing these things at very high-speed flows, measuring temperature, velocity, mass and momentum. The mass flux is just the density times velocity. Momentum flux is just momentum flux, and that's the thrust in some cases. Then we learned that, well, we can measure multiple things in real devices like combustors, and we can measure, we did combustion control around 1998, first laser-based control of combustion. once we found out we could measure one or two things, we started measuring 3, 4, 5 things. And then since then, there's just been a lot more applications for devices and practical problems and so on, and now including flight engines. Well, let's see, I have somebody here from Colorado, so this is my student, Professor Rieker, Colorado, one of my strong students. There's a lot of history to tunable diode lasers. Now we have at least one student here doing diode lasers. But it was 35 years before we finally got to what's called high fire, conducted in Australia. But people were using 8 tunable diode lasers to probe a combustor it was done by the people at Wright-Patterson Air Force Base, but it was actually executed in Australia. And I believe there's other people doing this sort of thing around the world now. So this was my idea that I had about 20, 25, 30 years ago, which I referred to earlier in an earlier lecture, that if you could imagine, at the time we could only buy lasers that had a few wavelengths. You always had to get lucky and find a wavelength that would match the spectrum. But over time, it gets better and better and better. So I imagined, at least, we would have lasers at many colors, or we call them colors, that would propagate by fiber, and we could probe different parts of a scramjet combustor. The inlet, propulsion engineers want to know how much air is in, how much fuel goes in, how much thrust do you get. That's what they want to know, which means how well did they burn the fuel. So you might care about the temperature. So propulsion people care about how much air is coming in, what's coming out, what's happening inside. So if you probe a few of these species and you accept the line of sight measurement, which is an path integral, you can learn what you need to learn about these devices. Temperature, velocity, water, CO2, and so on. That was a theme. So we started this a long time ago, and we built a prototype, tested it at Stanford, and tried to take it somewhere else. So 3 of my students and a research engineer were at Caltech for 2 weeks just recently. But they came back from the weekend, measuring in a hypersonic shock tunnel. So we have field campaigns. Students put together the system, they go and they try these methods elsewhere. So that means the systems have to be portable. And gradually they're being used in flight. So basic idea is line of sight absorption, laser at frequency nu. You scan the laser across the line. Why do we do this? Because we want to scan across the line and take advantage of the information content of that shape. Or we want to get the integral. If you had a monochromatic laser, you wouldn't be able to scan. So you need a tunable laser that can be scanned so you can take advantage of the integral, the line strength, independent of line shape, to get at the concentrations. So the Beer-Lambert law applies whenever it's monochromatic light, whether it's a small molecule that we think about, well, here's a big molecule, so we're doing this with a cross-section. If it's a small molecule, we think about line strengths and shapes, mole fractions. If it's velocity, we simply angle one of the beams through, and we can see the shift in the absorption line position. So this is the shift in the wavelength of the laser needed to absorb light for that moving gas. And as I mentioned, we've done this for velocities as low as a few meters per second and as high as 15 kilometers per second. Temperature is always important for reacting systems, and we'll use the ratio of 2 lines. So you take the relative ratio of the alphas or the K nus, and you can get to the ratio of the number densities, which gives you the temperature. We finally learned that, well, why don't we use more lines? Let's use more lasers and start multiplexing and try to measure things simultaneously. One interesting thing is the usual question you get when you present absorption to people who do combustion is they'll say, well, how do you deal with the non-uniformities along the line of sight? Can you ever do turbulence? No, we can't do turbulence. We can't get millimeter spatial resolution because we have a path integral. But I had 2 students who addressed the question. If you have a temperature non-uniformity along the line of sight, can you interrogate it? And the idea is, well, you add more lasers. So if you add enough lasers, each of which has a different sensitivity to temperature, then the path integral reflects that superposition of effects. And so the students would say, scan 10 transitions with one laser, 10 transitions, look at the fractional transmission, and from that you can infer what temperature distribution would cause that outcome. It's like saying what fraction of the beam is in this temperature range or this temperature range. So you can't say where there's a cold spot, but you can say if there's a cold spot. So we have made some progress on this question of non-uniformities along the line of sight. There's two main strategies. The one we call scanned direct absorption. So you scan the laser. The laser is usually scanned with a waveform of current. The current through the junction causes the intensity and the wavelength to shift. So when you scan, and that, you might do this over a time of, say, 1 millisecond. So if you scan over a millisecond, you'll see the absorption line. So the background is I0, and this absorption line is here. There's another little one right here. Now you take the logarithm and you get the absorbance. So that's called scanned DA, scanned DA. It's simple, smart thing to do if you've got enough absorption. But there is an alternative. It's called wavelength modulation spectroscopy, or WMS. And that technique, you do the same thing, except you superpose on that scan very high frequency modulation. So you actually scan dithering as you go. And then if you take the transform, Fourier transform, you get something like this. And you can choose whether you want the 1F, the 2F, the 4F. You can choose which frequency. You do the analysis, Fourier analysis, and you record this. The 1F would be the slope of the line, basically. 2F is like the derivative of the slope. So this looks like the second derivative of the line shape. And when you do something like this, it rides kind of the zeros and the wings. So there's some benefits. So the WMS has many advantages for small signals when you have a hard time discriminating the small difference. If this difference is small, it's hard to compare I and I0. And the WMS is sensitive only to shape, so it has some advantages. But with an advantage, there's always a disadvantage. WMS is great for removing noise. And then we came along with the scheme. We thought we invented it, but we didn't. Somebody else invented it, called the ratio, 2F over 1F ratio. So if you take the 2F signal and divide it by the 1F, both are proportional to laser intensity, and it cancels out laser intensity, even when laser intensity is being modulated by losses in the system. So it was a great idea. We weren't first. So and this is a demonstration of how this works. And so we took a laser here through some sort of a lens to get a collimated beam, and over here a detector across the room. I guess it was about a foot. And we saw in the room air, you can see water and CO2 without too much trouble. So we just looked at the water that was in the room over a foot, 6% relative humidity that day, 6% absorbance. So you see quite a bit of absorbance. And now you can do things like, well, what if you block the beam a little bit with a razor blade? What happens to the 2F signal, 1F signal? The ratio stays constant. But this concept of if you have losses due to particles or dirty windows or vibration, if you take the 2F over the 1F, you remove that problem. And that's a powerful idea. So it works when the beam is attenuated due to scattering losses. And it also works, we showed that it worked when you do it by vibration. So we pound on the table or do something which is a transient blockage of the beam. So the 2F over 1F WMS is a good idea. And it also solves problems when you go to a real device where there's windows. Windows are a problem. What if the windows get dirty, they vibrate, something happens, particles present in the flow? This idea gets rid of that problem. Oh, okay. Now, let's see. I usually say at this point, the benefits are obvious. What are the downsides? It's say 20 times more sensitive and 20 times more complicated. It means there's 20 times more ways you can go wrong. I look at the scan DA, I look at this, I know what it means. I know exactly what it means. I know how to look for what's going wrong. WMS I've never had a good physical feel for it like some of my students have. Greg Ricker was really good at that. He almost gave up on his PhD when he stumbled off some of the challenges, but he mastered it. Okay, so here's the spectrum of NO, CO, CO2, and water, and then a fuel. And just to remind you that small molecules we think of as discrete transitions, discrete line positions, and spectra. So even the water, which looks like it's a complete, fully filled up space, there's always space between the lines. It's just that we can't see it on this diagram. So there's almost always spaces between the lines, although there may be interference. The biggest problem with water is if you want to measure NO, if you're here, you got to worry about water. CO, you're here, you got to worry about CO2 and you got water. So you have to understand the positions of the lines to pick say a CO transition that's in between the others. So that's the problem, but we know how to deal with it. Big molecules, we do a different way. We do it with cross sections. So you might ask, well, can you buy lasers at all the wavelengths you need? Well, when we started around 1990, I did this. Well, I did it in the infrared in 1977. But by around 1990, 2000, it started getting better and better and better. So gradually over time, you can buy lasers at any wavelength because it's really a materials problem. If you have a big enough market, they can find a materials composition, which allows the laser to function in some structure. So there are different, we got quantum cascade lasers here, somewhere, there it is. So as you change wavelength regions, you change the band gap. The band gap is determined by the properties and the thickness of the layer. So it's all about material science and fabrication. But nowadays you can buy almost any color you want, ranging from, well, there is a problem down here. The shortest you can get with a CW diode laser that's not frequency doubled is probably around 750 nanometers. And there's reasons why I'd like to be a lot shorter. But as you go up in wavelength, you're changing the band gap. I think you can get out to about 15 microns now if you have enough money. You know, the fewer there are, the more you have to pay. And it's all about materials. So now the initial stuff was right in here. The initial telecoms were right around here, and then they were up here. So for a long time, we worked right in here. You could buy, everybody measures water at 1.4 microns. There's a reason why. But now you can get more sensitivity out here. So if you're doing HCN, you're out here somewhere. You can buy those lasers. And therefore, you can access many atoms and molecules. We always want something we can't get, but we can do most things. And of course, they're packaged up in nice form. They're fiber coupled. You could beam light through fibers. Well, you could beam light through fibers at most wavelengths. Fibers are not as advanced, actually, as the lasers. So now lasers and detectors, you know, they look like this. They can look like a little, canned device here. Or they might look something like this if you're having a quantum cascade laser or meerkat laser, say. Now, when you change the wavelength of the light, you have to change the response of the detector. So you use different detector materials for different wavelength regions. These are what would be called quantum detectors. So they have the ability to respond to a single photon. They may not respond to every photon, but they respond to individual photons. Those are quantum detectors in comparison with, say, a thermal detector. If you only want to measure power, you might only use a thermal detector that measures the power on a surface. So the wavelength range would determine the detector type you would use. Another characteristic is if you want to go to long wavelengths, you may use what's called a mercury-cadmium telluride detector. Indium antimonide is degrade out to about 5.6. Then there's the area of the detector, the bandwidth of the frequency response of the detector. A lot of questions about the detector to do your experiment that you've set out to do. So there's this is useful for your material you carry away. There's the bandwidth. So let's say you want to do something really fast. You want a high bandwidth in hertz. You might use a photomultiplier or a Mercad telluride detector. They can be megahertz detectors. Some of them are not so fast, lead sulfide. So there's you do the spectroscopy, you figure out what you're trying to do. Now you got to pick the laser, you got to pick the detector, and you have some electronics. So there's different parts. So one way of thinking about the detectors is, well, how well do they perform? And there's a parameter called D star, which is a measurement performance parameter, which is, the main thing is this 1 over the noise equivalent power. So what you want is a high D star, which means low noise equivalent power. You want, how low a power can you sense? It's characterized by D star, and then typically when you buy these detectors, they're either cooled or uncooled. If they're uncooled, they work at room temperature. If you cool them down, they'll have lower noise. They're a little more complicated. So detectors are often cooled. Some of our detectors are cooled with liquid nitrogen. So this is just to remind you that there are properties of the lasers, properties of the detectors that go into your experiment. Okay, I'm going to show you some example applications. Remember, we started in the near infrared. We gradually worked into the mid-infrared, which is much stronger. And the reason is that the mid-infrared has stronger transitions. So you do HCN at 4 something rather than 2 something, which would be the first Overton. Okay, CO2. So you're interested in CO2. This is just a partial spectrum. You might say, well, CO2 has different bands. Look at this. So we have the 2 nu 2 plus nu 3. So now you have learned that those are absorption transitions. They correspond to 2 changes, 2 quanta of nu 2 plus 1 quanta of nu 3 all at the same time. Over here is nu 1 plus nu 3. So CO2 being triatomic has multiple bands. Yeah, but look how much stronger this one is than these. So, clearly if you want to measure CO2, you do it here, not here. Not shown is the longer wavelengths, which are even stronger. So if you can get even more sensitivity if you get to longer wavelengths. This is an old slide. So we did a lot of work at 2.7 for many years. We worked at 2.7 because you get 2.7. It's more expensive to get to 4 microns. And that's already pretty good. So if you wanted to measure temperature, which is very important, you would calculate the spectrum and you'd identify a pair of lines that gave you the temperature sensitivity you want. How would you pick those? Well, they have to be strong enough, and you want the ratio to be temperature sensitive, which turns out to depend only on the difference in E double prime. E double prime is the energy level of the lower state. E prime is upper state. So what you want are states that have large differences in E double prime, and they'll give you the best sensitivity. But if you spread it too much, one will be weak and one will be strong, and you have to kind of take that into account. So we picked for a long time, we did this, R28 and P70, which have really desirable properties. So if you're within one vibrational band, all you can play with is J. But what if you measure in 2 different vibrational bands? That turns out to be the best of all because the E double prime changes by the vibrational quantum. So you can get even higher sensitivity if you measure different V's, which I did. So here's the shock tube, and I have this in here. It'll be of interest to the people from KAUST. This was the setup that Amir Farouk used. He was my student at KAUST. So our goal was, I had several students, and I said, let's see how well we can measure temperature. The goal was, can anybody measure temperature to 1% in real time? That's a target. So we do this experiment behind a reflected shock wave up here. We use the shock wave. The reason we use the shock tube in this case is if we measure the shock speed, we can calculate the reflected shock temperature to 1%. So it's an experiment in which we know the temperature to 1%. How do you do this at 3,000 degrees Kelvin? How do you produce known temperature to 3,000 Kelvin? Too high for thermocouples, too high for a static cell. So it's a way to produce a known temperature. And now we're going to use WMS. Okay, we're going to modulate at 40 kilohertz, no, excuse me, 100 kilohertz. Two lasers. So there's a laser here and a laser here and a laser here. So we picked these two colors, 2.74, 2.75. That's when we were using the 2.7 micron band, which is a good band. Not as good as 4 microns, but it's good. And we modulate them and we do WMS. And then we do the data analysis at 4 kilohertz. So when you do this, the first thing you have to ask is, how does the 2F signal ratio, peak signal ratio, he was not scanning, he was doing fixed wavelength. So that's the temperature sensitivity. So you can see about what you'd expect to do, and it was pressure insensitive. So how well did it do? It's sensitive to temperature, and you want that to be as sensitive as you can make it. So for example, you want to say that if I could measure the ratio to 5%, I'd measure temperature to 1%. That's what you hope for. We hear about accuracy, precision. Okay, this is his, now this took like 2 years. 2 years for him to get to this point. Well, there's a lot to learn. So he did an experiment behind a shock wave. So this is time. So that's the incident shock, reflected shock, and the blue is the pressure. So there's a little bit of a dip that's, I won't go into that, but there's a constant pressure for 9 milliseconds, which implies constant temperature. And now he takes his inferred temperature. A little bit noisy at the shock front. Here's his inferred temperature. Okay, this is blown up. This is the best we've ever done. So you don't do this every day. But he eventually got to this level on one day. We measured the temperature to within a few degrees Kelvin. I don't think anybody's ever done it better. So that was a case where we knew the temperature, we measured the temperature, and we got to within about 3 degrees. So we then used that, students used that, to look at an interesting problem. It was the shock wave in an aerosol. So now I'll explain this. This was a fuel aerosol. We produced a fuel aerosol, a cloud of small droplets of fuel, and we send a shock wave through it near the end wall. So what do we see? We see this is now the extinction. So the light is extinguished by the particles and absorbed by the molecules. So here's her transmitted intensity. Transmitted intensity, now intensity this is extinction here, excuse me. So we see some extinction. There's the cloud, there's the extinction. The shock wave compresses, so we get some increased extinction. And then we see the extinction signal go down to near zero, and there's a reflected shock. Why does the extinction signal go to zero? Shock wave through fuel aerosol of small size. What do the droplets want to do? Evaporate. When they evaporate, there's no more extinction. So what we found is we could actually monitor the extinction, the time dependence of the extinction. So we've created an experiment in which we see the initial droplet loading, we see the droplet extinction when you've compressed the mixture, and then finally it goes away. So we measure the evaporation rate. But we're trying to measure temperature. What we wanted to show is that you can measure temperature even in the presence of droplets. So here's now his result for temperature. We're down here at 300 degrees. We jump up to the right behind the shock wave before it evaporates, and then the temperature goes down. Why does the temperature go down? Evaporation. So basically, we created this experiment where we know the initial he we measure the extinction, which tells us that if we know the cross-section of the droplets, we can say how many droplets are there. What he proved was we could measure the temperature even in the presence of droplets, which is pretty important. Practical problem. And I left that in there because that's Professor Farouk that did that for me years ago. So the 2f over 1f idea is really powerful for flows that have particles and bad windows. It's just that you have to really be sure you know what you're doing with the electronics. Okay, I looked at, now moving on to aerospace to satisfy my Air Force sponsor. We did a series of things that are propulsion related. We measured velocity at Stanford. We did this in a wind tunnel. Superflying velocity at NASA Langley, University of Virginia, and so on. So we've been to a lot of different places. Scramjet testing, that was Ray Grieker. So the simple configuration is you bring the laser beam in and you cross it. So one has a Doppler upshift, one has a Doppler downshift, and all you have to do is measure the difference in spacing. It's not an absolute measurement, it's a relative measurement. That worked really well. Why? Because there's water everywhere. We got down to about 2 meters per second. Maybe less, about down to about 2 meters per second. So, and of course, in the wind tunnel, we knew exactly what the velocity was. So we were trying to prove we could measure this at low speed. This is not the way you would measure velocity in low-speed airflow, but we just were testing. The real application is in high-speed flow. So we went to NASA, well, the student went to NASA Langley. This is their direct connect vitiated tunnel. So they heat air with combustion. So you put in a little bit of combustion, heat the air, get it up to about 1500 Kelvin or so, send it through a nozzle and an isolator, and then finally it's ready to go into the combustor. So what they wanted to test were, it's just a high temperature wind tunnel in which you want to use air and you want to test its behavior, either flowing over a body or combusting before it's a nozzle. So this is a NASA Langley test called the Direct Connect Supersonic Test Facility. They were working when we were there at about 1,000 Kelvin and about 0.7 atmospheres. That corresponds to Mach 5 flight. And the student built a translational rig. So this is here's the translation stages. So he had his lines of sight and he moved them during the course of the experiment over a second or so. And we put this in the isolator section. And he wanted to measure the temperature and the mass. This is like what is going into the combustor. You have to know what's going into the combustor to do your combustor test. So he had his translation stages. He took 2 trips. He built this for about 2 years. Then he went there and he took 2 trips, worked great. We also went to, oh, here it is. This is the NASA Langley test, just some more results. We were scanning this way and this way. It was about a 7 by 13 centimeter test section. And the good news is he was able to measure the velocity at fixed locations and compare it with their CFD codes. And we got really good agreement. Lei and Chang was the name of the student. I guess it's 11 years ago. But we also could measure transients. They did not know how to measure transients. So they had a sophisticated CFD to run this tunnel, but they couldn't measure the transients. But basically we found good agreement after the transients. Then we had these are field campaigns now. So we went to university. Anybody here from the University of Virginia? Okay. We went to the University of Virginia where they have a electric heated supersonic tunnel. It's pretty small, but it is electrically heated. So they've got down below big bank of electrically heated, I don't know if it's pedal bed. I can't remember the structure, but they heat air to some temperature, and they bring it up, and they're trying to simulate this Mach 5 flight condition. But their test chamber is really pretty small. Here's the combustion taking place. I'm not sure if this is going to make a noise when we do this or not. Maybe not. Let's see if I can do this. I'm sure if it's supposed to do this. It's not doing this for me. Okay, when you go to a place like this, there will be the test cell, and then people are in another room, entirely different room. There's a lot of safety questions, and they had a big this is an expensive thing, but now you've got steady supersonic flow. You're processing a lot of air. So this system is really small because it's expensive to do these things. But then they have people who do scramjets know that you have a recirculation cavity to get flame stabilization. And we wanted to make measurements. Let's see, anybody here from UCLA or UCLA? That was Professor Spear, was one of the people who went on that one. And let's see. Purdue, we have Purdue. Yeah, so Chris Goldenstein. So Goldenstein and Spear did this measurement campaign at the UVA. So, you do it in the lab, that's one thing. Now you got to put it in your suitcase, take it to UVA and make it work there, the challenge. But they did it. So they were measuring CO, it's a combustion experiment. So you want to know water, CO, and CO2 to characterize how much combustion is taking place. And they used some fibers, and they were able to measure two-line temperature and so on. But it's not exactly uniform. It's fluctuating like crazy. And of course, that's part of the question. How does it agree with CFD? They measured it at a few different locations in that across. And then they measured as a function of position, distance from the lower wall, distance, and compared. What did we find? General agreement with CFD, but not great. So the whole idea was to use the measurements to validate the CFD, or to guide the modifications to the facility. Anyway, they measured CFD, they measured CO2, and did well. They were more accurate on the CO2 than the CO. Okay. Okay, now we're going to go to, this is Wright-Patterson Air Force Base. 15 years ago, I forgot. That's Greg Grieker. He went once or twice. That's I think they call it Tunnel 19 at Wright-Patterson. So it's a big, vitiated combustion tunnel to test scramjets. So the heat expand through a nozzle, and then they flow the gas through the combustor, introduce the fuel, and see how well it burns and how it mixes. So they want to measure how well it combusts. One of the problems with scramjets is if you release too much heat, it causes what's called unstart. And the shock wave will come back up, or instabilities will come back up, and it'll cause choking of the inlet. So one of the discoveries was, Greg found, now this was interesting. He used four lasers, 2 pairs. Each pair gave him temperature. So we got 2 temperatures. One pair is sensitive to low temperatures, one pair was sensitive to high temperatures. And what we wanted to look for is how well we could measure temperature, and when did those temperatures change, because there was getting some cooling along the wall, a precursor to unstart. He used WMS. He mastered this. And but interestingly, he didn't measure the absolute temperature. He measured fluctuations. The whole idea was that if you could measure the fluctuations would tell us it was about to unstart. So there's this plot of this temperature versus time for the 2 sensors working at high speed. So what happens is at about 40 seconds, these things run for minutes. At about 40 seconds, the temperature is separated. So that was looking along the site, and he was seeing that there was not a single temperature. There were effectively 2 temperatures, and that meant it was about to unstart. But he didn't actually, here he plots the temperature, but it was really mostly looking at the frequencies. He ended up looking at the ratio of the low frequency signals and the high temperature signals in the low, and he could see when this was coming, and he called that the onset of instability. So sometimes it's only the frequency content of the signal that you care about. Sometimes it's the absolute temperature. That was a new paradigm for control. We still think about this, actually, measuring the frequencies of water signals. So in a scramjet, the problem is if you put in too much fuel, it'll thermally choke. It'll choke, and then it'll send that signal back up and choke at the inlet, and you lose performance. You want to put in as much fuel as you can, but if you've been too much, so we have this idea for controlling unstart. Okay, future trends. More and more people are doing tunable diode. More and more people are doing this. Good. Around the world. We're getting closer and closer to practical applications like flight. Already it's used in, say, monitor the output of a gas turbine combustor or something like that. We use it in one of my students went and monitored NO and CO in 100 feet in the air in a coal burning power plant. So you have to kind of live in that environment. And then, let's see, what else? One of my students built a system to measure in a coal-fired gasifier in North Carolina. And it was up in the air, high-pressure duct. And once he installed it, he left it there for 2 months. And it just kept working. So we're closer and closer to being able to view these as practical systems for combustion or process control. And of course, they're most often used in research in energy or propulsion, or what's your subject area? It's kind of a research. So basically, you could use this in fire environments. I think Greg Rieker at Colorado, he does some stuff on fire, fires also. Fire is popular right now. So we've done some work on IC engines. In fact, we have a new project on IC engines. We had a project with, we had a project on, oops, that's my last slide. We had a project in a real engine, a production engine. And we were, Nissan was the company. And we were supposed to measure inside the engine the temperature in the vicinity of the spark plug. So we built a little gizmo and did it at near Stanford, and then we went to Japan. And this thing worked really well. So we measured temperature, fluctuating temperature near the spark plug in an engine. And then they asked us to measure the fuel-air ratio as a function of time during cold start. So when you first start the engine, that's when they have the unburned hydrocarbon emissions. We could measure that for them. Actually, measuring hydrocarbons is really easy. The absorption coefficients are so big. So we've done engines, and we got a new one. I won't tell you the name of this company. We got a new one now for a company that makes racing engines. And they want to characterize accurately the inlet manifold and the exhaust manifold really accurately to refine their fluid mechanics models that they're using to optimize their engines. So we've been in engines, sliding coal gasifier. That was a tough one because you have to go through this walls where there's slag is coming and going, and it's a problem. We finally got that to work. National Carbon Capture Center, and students have been to some interesting places. All right, almost on time. So what do I try to tell you with the diode laser story is? The spectroscopy is pretty simple. The equipment is getting better and better. It's getting more and more robust, and it's very practical. You know, you can actually, well, my story about the oxygen sensing is when I bought my oxygen lasers for O2 in 1990, they were $7. Unbelievable. They were mass produced, use $7. But now, of course, when we want to buy one at that wavelength, it's like 2,000 because they don't make very many. But still, it's all materials, and they can do this. So we're going to see more and more of this. More and more engineers are going to use spectroscopy as well as pressure gauges and thermocouples. That's the idea. Yeah, question?
What's the advantage or disadvantage for using your DLS for sensing at high rep rates versus cars or?
Okay, so I always get this problem. I always get this question. So we have this big competition. Who can measure temperature the most accurately? And the cars people will say that they can measure temperature 1%. I'm not sure it's true, but anyway, cars is typically a pulse laser method. It has the virtue that it's more of a point measurement. It's usually not continuous, so they don't get the same kind of frequencies that we do. But basically, their claim to fame is they can work in hostile environments. They can make semi-point measurements of what? Well, of species, CO2, nitrogen, hydrogen, of species that have Raman spectra. Equipment is a lot more complicated, But it is a measurement at a point, not a line. And if you look at the structure of the signal, you can get temperatures pretty well. And that's a hot area. Well, it's a good area. good area of how accurately can you measure temperature and composition by various forms of cars. And there's femtosecond and so on. That's a hot area, but it's harder. You don't put it in a suitcase and go down to Southern California like we do. So you pick and choose. So I would argue that they'll look at shapes of the spectrum to get temperature. We look at shape. We look at ratios. It's kind of the same idea. You're basically looking at Boltzmann ratios. So if you can collect, but now you have to collect the spectrum. So you got to have your lasers and cross beams and get the spectrum, and so it's a lot more sophisticated. It has advantages though. You could imagine it at really small points. We can't do that. So, but it's Raman scattering. It's not absorption. Our process is a so-called linear process, and their processes are nonlinear processes. That's another complexity. Yeah. Yeah.
Look at the fluctuation.
Yes.
I'm guessing that if your flow dynamics are of the order of thirds or whatever, and talked about having better paradigm,
Yeah.
but your actuators cannot do more than.
Yep.
So what are your comments on how you think you do something like?
Yeah. Yeah. Well, yeah. Good question. Good question. Well, I'm not an expert on that aspect. So my idea, which we haven't actually proven in a real device, but we did it in that combustor. We just looked at frequency content. We didn't say what's causing this unstart. We just said we can see it. In that case, it actually evolved over time. There was plenty of time. So I don't know how fast the unstart thing is. I don't know that it's true that it's kilohertz. So my mental picture is you're getting some starting to choke, and the water the signal's coming up through the boundary layer, I think. And I don't know how fast it moves. That's an interesting question. But I know we can at least see it. Somebody else is going to have to worry about, what they're going to have to do is they're going to have to suddenly reduce the fuel flow. That's what you have to do. So I think that's a good question. How fast can you modulate the fuel? I think you could probably modulate the fuel up to kilohertz. But yeah, that's a practical question. I don't know the answer really. Yeah. 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 Okay, so when we use the word extinction, we have a cloud, we have an aerosol shock tube, we have a way of producing a cloud of droplets. And you get scattered, we'll call it scattered light. Actually, there's a little bit of absorption by the particles, but it's mostly scattered into different angles. So you lose light, we call it extinction. And you can relate that extinction back to the volume of the particles. I wasn't so interested in that. The question was, can we measure temperature of the vapor, even in the presence of particles, whether they're droplets or soot or whatever? So, because that's a problem. How do you measure in a flow that has extinction? I don't know if I answered your question. So you could use the same technique to study evaporation. In fact, initially my plan was I was going to have a cloud and I was going to bring a shock wave through the cloud, a fuel cloud. And I wanted to study the formation and structure of detonation waves. It took 10 years to figure out how to produce this cloud, 3 PhDs. By that time, no more money for detonation. So, but I did, and then I found that we looked at multiple colors as the shock wave went by. And the extinction of the different colors changed differently in time because they were sensitive to different diameters. So I figured out we could infer the evaporation rate and the sizes of the droplets because the small droplets would accelerate faster than, okay, we could do that. Then I realized, we could calculate this better than I could measure it. Sometimes computations are better than experiments. You can calculate it with less uncertainty than we can measure. Measurements are hard. So we look for the place where you have to have the measurements. But I think, yeah, there's some interesting problems in evaporation. Any other questions? Okay, so we've just finished lecture 9. Next time, I wanted to increase the combustion really is reactive systems. So combustion gets a dirty connotation to it. It's really just reactive systems. So we do a lot of things that relate to just energy, efficient use of energy. Hydrogen, so it's not fair to give the word combustion such a negative connection all the time, because there's clean combustion as well as dirty combustion. So I'm going to talk a little bit about energy in the next lecture. Okay? Okay.